Okay, good evening. Welcome everyone to the IMS Uncombined Public Lecture Series tonight. We are very fortunate to have Professor Casselman from the University of British Columbia to be the speaker for the public lecture this evening. Professor Casselman studied at Harvard and received his PhD from Princeton. Then is currently Professor of Emeritus of Mathematics at the University of British Columbia. He has a very distinguished career, has done outstanding work in representation theory, geometric combinatorics, and things related to Langland's program. In fact, I think he's one of the prime movers in putting many of Langland's work on the internet. But in addition to this, he's got very, very wide interests as well. He teaches computing, computer graphics at the university, among other things. He was for a long time, 16 years, the graphics editor for the notices of the American Mathematical Society. Professor Casselman was an invited speaker of the International Congress of Mathematicians in 1978. He's also a fellow of the American Mathematical Society. So tonight he will give us a lecture with the title Mathematics in the Solar System. Please welcome Professor Casselman.
I should explain first of all that mathematical astronomy is a hobby, a profession in mathematics is something quite different. Professor trying to explain. So if it looks like an amateur production, then in some sense it is. On the other hand, mathematical astronomy is an extremely attractive subject. It's very complicated, it has some popular appeal, and I like to draw pictures, and you can draw an infinite number of pictures concerned with mathematical astronomy. So, the mathematical astronomy, well, the mathematics applied to astronomy is a very old subject, perhaps one of the oldest in mathematics. Not quite the oldest, but one of the oldest. It began in a theoretical way roughly 600 BC in what is now Iraq, in the city of Babylon, as far as we can tell. I'll show that a little bit later on. But before I explain more about Babylon, let me show you some very simple pictures to show you what things are all about. So, in order to understand what the Babylonians faced, you should understand that they began by just looking at a naked sky, so to speak. It's no features at all, except you see stars located here and there all over the place. And occasionally, you see something more. And so, faced with these stars, you want to label them somehow. You want to begin to organize the universe. And what we do nowadays is we have a name system of the stars. These names are actually mostly, they're Greek, Latin, and Arab. They're not due to the Babylonians at all. I don't know what the Babylonian names of stars are. The Babylonians did, as far as I know, name the stars, but what's really more interesting is, from a historical standpoint, is that they named all the parts of the zodiac. And in fact, the Babylonians, it seems that their major interest in mathematical astronomy was because they wanted to do astrology for the king. And to tell you the truth, there is a direct line from Babylonian astrology to current astrology. It never stopped. Even the same language is used after 2,500 years. Anyway, the Babylonians did not assign coordinates, as far as I know, to the system, although they must have at some point. But this is something which a little bit later than the Babylonians, the Greeks inherited all the data the Babylonians had accumulated. And they assigned a coordinate system. There are two coordinate systems. One of them is the horizontal line you see, just running straight across like this. I'm glad to be here in Singapore because it's so close to the equator that I don't have to explain all the complications that come if you're in the northern hemisphere, in which case you see a very, very different view. Here, you can actually see the equator all the time, and the view you get in the sky is more or less this. I've drawn the picture in such a way that it rotates, so this goes from 0 to 360 degrees, another 360 degrees, and so on. You'll see why I've done that in just a moment. But however, there's another, so this is the XY plane, so to speak. You're looking at a two-dimensional slice. Then there's another coordinate system that works like this. This is actually the intersection of a plane with a sphere, but when you draw things like this, it comes out like this. And this is the plane of the sun traverses in. So it's a little hard to see how the sun does it, but theoretically it can work out. The sun goes through the system. So here's something you can see. Here's something which the Babylonians faced and had to deal with quite often. They were very interested in when they were next going to see a moon. And so you can see the moon rises across the ecliptic every month, in fact, something like that. And that's what you get. So that's the first thing the Babylonians were very concerned about, was sightings of a new moon. In fact, so mathematics is a history of problems. And if you ask what problem was it that mathematics of the Babylonians was applied to, the answer is there are certain astronomical events that occurred, such as when you can first see a new moon, and they wanted to know, when do you next see a new moon? They spent an enormous amount of energy and time and ingenuity actually figuring this out. They did a reasonable job. You might think it's a trivial job, but in fact it's very hard to tell whether the next moon is 29 days from now or 30 days from now. It's not at all a simple exercise. You have to be able to plot positions of the moon in some sense. Just to convince you that I wasn't exaggerating about the sun, I have another. You can see the path of the sun. So, of course, you can't actually see the background of the stars while the sun's there, but it is possible to work out where it has to be by extrapolation of some kind. The Babylonians also knew about the planets. I gave up the black background for a while. It's a little confusing. What we're looking at here is the trajectory of Mars through the sky. Let me go back again, just to start over again. So you can roughly see that it follows essentially the same path that the sun followed, or the moon followed. They all generally follow the ecliptic. Mars has a couple of special features, however. Watch carefully. It goes backwards from time to time and circles around and goes on. And after a while, after an odd number of days, more than a year, it goes backwards again. Does a little loop, keeps on going, and does a little loop before it quits the screen. The Babylonians were extremely interested by this. It seems, I'm not sure exactly, they didn't write about that. It seems that the Babylonians thought that God was somehow trying to speak to them, and that this was some sort of calligraphy that he had in mind when he was doing it. And it was up to them to figure out exactly what the message was. They spent, again, as I say, an enormous amount of energy trying to figure out when. So again, the question was the same sort of question. Given a moment when the Mars begins to go backwards, when is the next moment that that Mars begins to go backwards? And that's not at all a trivial question. You can get a better idea of how things look just by watching it loop. If you actually track the path as it goes, it does look a little bit like some sort of funny calligraphy. It's beautiful, actually, in some weird way. It took a very long time, another 600 years, before people figured out geometrically what's going on that makes this work like this. We have no record that the Babylonians themselves ever tried to do it. But the Greeks had came up with a mechanism that explained very roughly what was going on, which was actually reasonably accurate for computing the things the Babylonians were interested in. And to give you an idea of, So here's another object. It's not a planet, it's a comet. And the dates, as you can see down in the lower left-hand corner, are much later. But the Babylonians also saw comets and recorded them. And if they attempted to draw a path, they must have been extremely confused by the calligraphy they found. In general, the idea I'm trying to convince you of that although we take things for granted nowadays, now that we have some understanding of the mechanism involved in the way planets and comets work, at the beginning of science, it wasn't at all obvious how that worked. Okay. So it is not. Oh, I know what's wrong. So as I've told you, this summarizes things I already said, emphasizes a little bit. You can see the pictures that I've drawn in close-up. This is exactly well, it's not quite the loops you're looking at, but there's something very, very similar. So that just summarizes what I've said. And excuse me, I'm not always completely familiar with this. So here's a sample. So the Babylonians recorded a great deal of astronomy on tablets. Many of you are probably familiar with that. They wrote on clay, and then the clay got buried. Sometimes the clay burned, in which case it lasted a very long time. So actually the astronomical records from Babylon between the years 600 and 50 AD are extremely voluminous. They're just, it's probably a large proportion of the tablets they wrote in astronomy have not been translated by anybody. Here's one that has been translated, and you can see this is from the British Museum. They've been very nice in recent years, though they didn't used to be. They've taken photographs of a lot of their tablets. This is on the internet. A friend of mine named Alex Jones found it for me. And here's a translation of what's actually on the tablet. So as you can see, their coordinate system was rather crude. 3 fingers below Capricorn. G Capricorn is a star in Capricorn. Mars being a little back to the west, the 5th, and so on. So it's not very detailed. This was early in the days. Later on, they got much more accurate and introduced some kind of coordinate system. But you can see they're interested in the retrograde, so it goes back and forth. They're very interested in how that works. The last refers to risings, which when Mars first becomes visible from behind the sun. So this is the first mathematics. As I said, the basic problem the Babylonians are concerned with was, given one station, what's called stationary. They call stations because the planet is stationary. It stops and then moves back. When is the next station of the same kind? It's not an easy problem. To show you what I mean, here's a sample of the intervals between. So I did some statistics. I'll explain where I got this from. We're looking at a number sequence, 764, 767, 776. They're all roughly the same magnitude. But if you try to predict the next number from what I've shown on the screen, you'll get in serious trouble. So it took them quite a while to figure out how to do this. In the end, the Babylonians did devise a system for making a prediction. This is not enough data to make the prediction. What they also realized was you have to know where in the starscape the station occurred. And if you record that as well as the interval, then there's some correlation they worked out and figured out as a numerical function. It's too technical for me to explain here. Actually, frankly, I have to confess, I don't completely understand it. But it'll come. However, as I say, we have lots of records of Babylonian astronomy, but they seem to have almost no interest in geometry. They were just interested in calculating, mostly sequences of numbers of various kinds. But the geometry, figuring out the geometry behind the astronomy you were looking at, was the main concern of the Greek astronomers who followed them. The Greeks benefited tremendously from the Babylonian data. The Babylonians made observations of things over a period of 600 years, which meant, for example, they knew almost as accurately as we do the length of a year, which is not at all a trivial calculation because it's very hard to measure where the sun is after a year. So it's not so simple, but they managed to do that. And they had all these recordings of the planets moving back and forth. So the Greeks introduced, well, a great deal of mathematics, which is very, very complicated, and a geometrical system to explain it. The most prominent of the Greeks was an astronomer in Alexandria named Claudius Ptolemy, who lived roughly 150 AD, and whose work, which was named by the Arabs who succeeded him, the Almagest, meaning the great book, remained the main resource in astronomy for 1,400 years, roughly up until Copernicus in 1543. The Greeks were concerned, again, with a limited amount of information. They didn't really care and had no way of knowing where in space an astronomical object occurred. There's absolutely no way of guessing. Nowadays we have telescopes, radar, rockets, all kinds of tools to help us do that. But it's extremely difficult to decide how far away an astronomical object is. The Greeks didn't bother with that. They had some rough idea, and they were content with that, but what they wanted to do was plot the two-dimensional points that you saw in the traverse of Mars, for example. And they had a number of mechanisms that explained that fairly well. Their measurements were inaccurate, and they probably didn't have enough money invested in astronomy in order to do a thorough job of observation anyway. And their predictions of angles suffered because they were not able to predict what happened all the time. They just knew they were able to record certain special events, like when things rose in the sky or sank in the sky, or when the moon had an eclipse of the sun. All these things they could measure. That limited how accurate they were able to be. Oops. There's a web page for the British Museum, the same tablet I showed. As I said, the British Museum has been pretty good in recent years. After a number of years, after roughly 1,400 years of people following Claudius Ptolemy, trying to improve, Ptolemy made a huge number of tables and did a great many observations. After 1,400, and all the time between that and Copernicus came along, his data was improved a bit, corrections were made, his own predictions constantly fell behind and lost accuracy. People were constantly working to keep things up to date, so to speak, mostly Arab astronomers after the Muslims took over Africa. And then Europe became interested in this, and the transmission from the Arabs to the Europeans is a little bit murky. But at some point along came Copernicus and decided he really wanted to improve Ptolemy. He did so in a limited way, but he did make one crucial point which people liked. I've looked at Copernicus. He's very hard to read his works. And it's very hard to understand why he's quite so happy with what he did. But a lot of people just took from Copernicus the single idea that whereas before Copernicus people thought everything moved around the Earth, after him people realized that actually the sun, or something close to the sun, was the thing that around which things moved. And that the Earth was actually rotating around in one day instead of the stars moving around. People had no concept of what it would take for an object the size of the sun to have to move around continually. They just had no feeling for what we now take for granted after we learned a good deal of physics. So Copernicus made that one idea, but he basically made no major change in technique from the Greeks and the Arabs. In fact, he complicated things a great deal because even more than the Greeks and the Arabs, he wanted everything to run in circles, not just a few things. And what happened then was there was a Danish astronomer named Tycho Brahe, who was a very wealthy man. He had an island that he owned completely by himself, and he had a huge and expensive observatory, which he started taking extremely accurate measurements of planets, moons, things, as often as he could. He spent all his waking hours, apparently, which are during the night, making observations of some kind or another. He was a rather weird character, but he did a really great job. And at some point, when he was close to death, he hired a German mathematician to work for him. The German mathematician was named Kepler, and Kepler, after an enormous and unimaginable amount of work, came up with 3 laws to describe the way the planets actually moved, which were very simple. So Kepler was the first person in the world, as far as I know, who attempted to figure out exactly how astronomical objects moved in space.
And it's an enormously difficult project. If you think of those pictures of Mars traversing, and you think, how in the world am I going to figure out how this, how far away is Mars? How is it moving? How can I possibly actually imagine what's going on in 3 dimensions? Kepler spent a good deal of time, used all of Tycho's observations, and after 5 years of very hard work and another 4 years of, more redoing his calculations to be sure it was okay, he came up with 2 of the 3 laws that are named after him. The first law is very simple and actually was a revolution. It's hard to imagine. People didn't know much about ellipses at that time. The Greeks had a great theory, but it was very hard to follow. And Kepler managed to show to his own satisfaction, in a kind of a sleepwalking process, that the planets move in ellipses, and that the sun is at the focus of one of the ellipses. I'll show you in a moment what an ellipse looks like. But you have to realize that both these statements are extremely revolutionary at the time. People up till that point thought that somehow planets were forced to move in circles of some kind or another. You just had to combine enough circles to get the planets to move right. And to say that it was an ellipse, which is a kind of a squash circle and not a circle at all, was a tremendously revolutionary fact. What's more revolutionary, and I hadn't realized this until I started reading Kepler recently, he said that the sun is at the focus of the planet system. Now again, we just think of everything moving around the sun, but at that time, the astronomers had some incredibly complex mechanism where the center of the universe was, the center of the solar system, rather, was not the sun, but some imaginary point very close to the sun. There were technical reasons for thinking this because they were forced to do that by all this circle business. So this is the first law of Kepler, and it made an enormous difference. Here's a picture of an ellipse for those who aren't too familiar with it. The key point is you have to know what a focus is. So first of all, an ellipse is a squashed object. What you take is very simple. You take a circle, and the circle is drawn here with a dotted line, and you squish it. You just squeeze it like that, and if you scale everything proportionally, you get an ellipse. What's interesting about this is, and the ellipticity, there's something called the ellipticity which measures the factor of squishing. You can see the factor of squishing is right there. So this means that this distance, which is called the semi-minor axis, is equal to the semi-major axis times this factor. This is the squishing factor. But the squishing factor, there's a number E which controls the shape of the ellipse. And if E tends to be small in the planetary system, but if E is small, then E squared is very small. And so the squishing can be relatively minor, but this distance here is proportional to E, and that's actually a measurable quantity. So what Kepler based his law on is the fact that he realized that, so the Ptolemy system worked pretty well for measuring angles, and his system was in some sense equivalent to this, but it didn't tell you anything about distances. So if I have a center, if the observer is here, then the distance doesn't change much as the thing goes around the thing. But if I have my focus here and the observer is here, then the distance is much less on one side than it is on the other. The place in the orbit where it does get close is called perihelion. Perihelion for Earth occurred a few weeks ago on January 2nd. Right. So as they say, it's some accident that the Greeks were so successful was that even ellipses with a sizable eccentricity are nearly circular. This eccentricity is 0.2, which is roughly the eccentricity of the planet Mercury, which has the most eccentric orbit in the solar system. Are there any questions? Okay. We'll see. The key geometrical property of ellipses, which most of us learn in high school, is that it has a certain distance property. If I go from the focus, one focus, to the diameter and then go back again to the other focus, that's a constant distance traveled. It's not clear that that plays a role directly in the physics, but it's a useful fact to keep in mind. Kepler then was concerned with, so now he knew very early on that the planets moved in ellipses, actually Mars. He only looked at one planet extensively and conjectured for the rest. He knew that the orbit was an ellipse, but he wanted to know how it moved in, what determined how fast it moved as it went around the orbit. And by a series of very complicated mistakes which canceled each other out, he came up with a second law, which says that the area swept out by a planet is proportional to elapsed time. This is very simple to state and very hard to use for computation, but he was able to do that too. Here's an illustration of how it works. these areas are the same, and you can calculate a rough approximation to the area by just approximating this by a triangle. What that tells you, for example, is the ratio of speeds at the two ends is 1 plus e over 1 minus e. And you can see that if e is small, then this is approximately 1 plus 2e. So it's the approximate ratio of the speed. So it moves quite a bit faster here than it did over here. Now, there are rules for calculating with this. And then Kepler had a third law, which was very useful, but I'll not say much about, except I'll refer to it vaguely later on. Basically, you know how the Earth moves. It moves almost uniformly. In particular, in astronomy of the solar system, the basic measurement of length is 1 astronomical unit, which is the radius of the Earth's orbit. And its period is 1 year. And applying a third law, that gives you the periods for all the others if you know what the semi-minor axis is. A few years after Kepler died, Newton came along and proposed laws of physics, which somehow explained all of Kepler's laws. He derived Kepler's laws as necessary consequences, and he extended them by showing that Kepler could be generalized to some extent. So Kepler only looked at planetary orbits, which are all ellipses, but Newton was more interested in a general theory, and he started looking at comets, which were easy to see in his time, as in ours. And he proposed that, well, you needed a generalization, so he pointed out that, in fact, hyperbolas and parabolas were also conic sections. They also could be orbits of bodies traveling in the solar system. But if they traveled in a hyperbola, then they would travel off to infinity. In recent years, we have seen, actually, things coming from outer space, passing through the solar system in a hyperbola and disappearing off into outer space. So here's just an illustration of the three different. If you look just at a piece of one, if you look at this piece here, if you look at just this piece here, then it's not easy to distinguish between ellipses, hyperbolas, and parabolas. So if you're dealing with a comet, it's very hard to tell which of the three orbits it's actually on. Oops, oh, sorry. Excuse my personal feelings. Okay, so there's a couple of more corrections to I have a little section on explaining which I'll pass over. One way in which Kepler's laws turn out not to be quite right. There's a very simple way in which they're not quite right, and that is that if I have two equal planets of equal size, then it's not like the sun and the planets. The reason the sun seems to stand still is it weighs so much more than the planets that it moves with very, very slightly. But if I have two equal bodies, such as you have in a binary star system, for example, they move around in an orbit around the common center of mass as their focus. Very nice. And you can see, shoot, I'm sorry, I keep doing that. So what happens here is one of the bodies is more massive, and this is approximately what happens in the solar system. You can imagine what happens if the body on the right is much, much larger than the one on the left. It looks like it's actually standing still. Newton was fascinated by Halley's comet. He drew a picture by hand, which I can show you. It's very, very nice. The internet is wonderful for some things. But what's more interesting is that, well, here's a picture of, oops, oh, sorry. No, I'm sorry. So, I'm sorry, you'll get a double image of it. It's my fault. So here's a picture of Halley's Comet, which Newton was really obsessed with, I think it's fair to say. So you can see that the thing which Newton had, which Kepler didn't completely understand, was the three-dimensional effect. So here's a picture of what Halley's Comet does. At the time of Newton, they thought originally that Halley's Comet was traveling on an hyperbola. As I say, it's very hard to distinguish them if you're close to the focus, if you're close to the focus. But in fact, it travels in an ellipse. So his colleague Edmund Halley figured out that the same, so you can tell sort of what the rough trajectory of a comet is. And Edmund Halley did this for a dozen or so comets and figured out that one comet kept returning, coming back every 76 years. And so he decided that probably it was on an ellipse, not a parabola. And then that's why it got named after him. Let's see. Then as time got on, things got considerably more complicated. This is not my own drawing. This is from a website of Wikipedia, which I'm showing you just to give you a rough idea of what the history. So at the time of Newton, all the planets out to Saturn were known, but none beyond that. The planet Uranus was discovered in the end of the 1700s, and the planet Neptune was discovered with a great deal of controversy much later on. And then about the same time, people started noticing that there were some very small bodies floating around in between Mars and Jupiter, and you can see them here. This is a modern picture of the asteroids. What's interesting about this picture, I don't think I'll have time to explain, is that they come in groups. The group called the Trojans, here's another group of Trojans. Well, the Greeks and the Trojans are sort of the same kind. And there's something called the Hildas, which are colored red. And then there's all the rest of the asteroids, a mass like this. At the moment, there are roughly 780,000 asteroids. It's a huge number. Most of those have been discovered in the past 30 years. I have to say, after searching on the internet quite a bit, I had trouble figuring out how a new asteroid is discovered. You can't just look through your home telescope and spot one anymore. You need some technological help, but I have to confess, I couldn't figure out exactly how that happened. There is a huge database of asteroids which tells you how to plot them yourself, but I didn't have time to do it here. What's interesting about, well, I'll come back to this picture and say something right now because I won't have time later. What's really interesting about the asteroids is the way they divide up. So these names are very interesting. It's known somehow, it was predicted, in fact, that the Greeks and the Trojans would be found 1/3 of the way around the radius from Jupiter. They're there because Jupiter's there. Even though Jupiter seems very, very far away, it's sort of created these zones where the asteroids collect. And that's also true of the Hildas. The asteroids are in some sense attracted by Jupiter, but the Hildas are repelled by Jupiter. It's a little hard to understand exactly how that works. I'll give you a hint later on of the mechanism involved. The Wikipedia page is actually quite nice, so if I did it again. So I'm going to have an interlude. I'm a little bit more than halfway through. There's one thing I want to show you. So these last diagrams of the Hildas, that was on Wikipedia, my plot of Halley's Comet and the comet which I haven't shown you, and my pictures of Mars and my picture of the moon. All those things come from a database which is maintained by NASA, which is very, very useful. To give you an idea of how things have progressed, here's the Nautical Almanac from 1922. Here's the title page. If you wanted to plot Mars in 1922, you would have to look at a table of this, which goes on for 4 pages. It's very hard to imagine anybody doing that, but people did it. And in fact, this sort of calculation, very serious calculation, began in the early 1800s. In those days, a computer was a woman who worked for very low wages with a lot of other women calculating tables exactly like this. So the terminology has changed a bit. As I say, the Babylonian astrology has come down a whole piece. If you Google the word ephemeris, as far as I could tell by looking over the first few pages I got, about half of them are concerned with astrology. Even nowadays in the modern world, that's the way it works. But the basic data source for astronomical items is something maintained by NASA and the Jet Propulsion Laboratory in the United States. I don't have time to explain how it works, but basically you can plot not any of the 780,000, you can plot for yourself or learn how to plot with their data any one of about 500,000 objects. You have to know what object it is because they don't have a nice search facility, but most of the time you have something in mind anyway. It's a very beautiful project. I don't know if Donald Trump has killed it yet, but he might have. But it's just a gold mine of information. I mean, if you want to know whether somebody's theory about this or that is wrong, you can usually find out by accessing. It's extremely flexible. So here I have it set up. So you can download the information directly to your page. You can plot over any length of time from almost any observation point in the solar system. And normally you get it plotted directly to your screen, but you can also have it downloaded directly on your computer. It's just a wonderful toy for those of us who like to compute obsessively. Okay, so now the second part is what I call chaos. So the first part is harmony. Kepler, after many, many years, Kepler understood finally the way planets seem to move, and they move in a very nice way, hidden from all previous people, and secretly unknown to, at least a secret to all previous people. But then, as soon as Newton came along and discovered the underlying cause of Kepler's laws, then people began to realize that Kepler's laws couldn't possibly hold. So Kepler's laws hold for all the planets as long as the planets don't interfere with each other. But they do, of course. Newton explained that gravity is a universal force which attracts between all massive objects. And so it can't possibly be, it's not very likely at least, that Kepler's laws hold and you can compute planet orbits at any time you want. And in fact, people realize this almost immediately by looking at comets more carefully. There's a wonderful comet called Lexell. So here is Lexell in 1755. This computation was retrospective, named after a guy named Lexell, a Swiss astronomer, who noticed that the comet that he was observing, I think 1767, was not behaving quite right, and he wondered why, so he did some retroactive calculations. Here's Lexell moving in 1757, 1758. Looks pretty reasonable, except you can see it crosses the orbit of Jupiter every now and then, and sure enough, sooner or later, in 1767, Lexell got hit by Jupiter, so to speak. That's not quite right, but I'll show what happened later on. And then it changed its orbit completely and went into a new elliptical orbit, which is quite different from the old one. But it didn't escape disaster this time either. It got hit and went off into outer space. I don't think anybody's seen Lexell since. It just disappeared from the solar system. It turns out that happens quite often. And so Kepler's laws really just don't cover the situation very carefully. Nowadays, this sort of behavior intrigues mathematicians enormously for reasons you can possibly imagine. Let's look more carefully at what Lexell is doing. So here's a picture of Jupiter itself. So now what I've done is I've changed my coordinate system so it's moving along with Jupiter as it goes around. I haven't rotated it, which I thought of doing. And it's a beautiful thing. So if you're standing on Jupiter, watching this happen, whoops. Yeah, that's what happens. So it's really nice. It's just following an hyperbola, but it's disappearing quite nicely. And the process you saw in the hyperbolic ellipsoid was used nowadays by NASA for all kinds of spacecraft exercises. Here's a spacecraft called Cassini, which eventually traveled off to Saturn. They didn't have enough fuel to put onto Cassini to get to Saturn. So what they had to do was to somehow figure out a way to have Cassini boost itself as it went along. And they do that by something nowadays called flybys or gravitational assist or somehow slingshot effect. So Cassini, the red path is the spacecraft Cassini as it took off from Earth. Earth is the outer one of these orbits here, the one that it's very close to. They sent Cassini into Venus, where it did a little hyperbolic trick and picked up some speed, and then it did it again, and then wound out to Jupiter, where it got again some extra speed, and then took off towards Saturn, which is the one it's aiming toward now, and when it got on Saturn, it braked and went into orbit around Saturn. So the standard technique, which you saw in Lexel, is actually nowadays an almost everyday event. Almost every satellite that travels a long distance uses some of the technique which you saw there. Then there's another example. Excuse me, I don't want. Somehow it got lost. Oh, here we go. So here is a picture of, well, I'm going to show you a picture of Halley's Comet. So this little gold thing is Halley, of course the scale is way out of sight. The rest of these are the orbits of the planets. It starts with Mercury, Venus, Earth, Mars, and then the outer four are Jupiter, Saturn, Uranus, and Neptune. And here's a picture of Halley's Comet speeding in. I had to plot it every now and then, which explains the slightly polygonal line. I'm plotting, well, you can see once every half year, once every 3 months, actually. So here's Halley's Comet. That's fine. It really does follow an ellipse, as Halley thought it probably did. Comes back again. Everything seems normal. Well, it's a little bit off if you look carefully. But now, as it comes out towards its aphelion, you see it doesn't actually follow the ellipse at all. And when you go around again, it deviates again from what it did before, even a little more erratically, I would say. It goes back in again and again. So we're looking at 76 years at a stretch here. And it does, and then I stop my simulation. What's going on here is that Halley's Comet is kind of passing a gauntlet. It's like, the gauntlet is the word used by the white men among the Indians of Northeast America. The Indians had this process. They would send a captive down a thing and they would hit him as he goes down. And that's what's happening to Halley here. It's passing a gauntlet of some kind. As he passes by the other planets, they move him one way or the other. And this is a very random event, after all. The planets are all traveling in different frequencies and different times and so on. It's a completely random event. You can imagine what Halley's Comet does over a period of millions and millions and millions of years. It just keeps getting hit, and moving around. This is actually the kind of process that people are, mathematicians at least, are fascinated by these days, because it introduces a certain random quality into the behavior of dynamical objects, which has become a major part of mathematics these days, actually. So, well, we've seen some of these. The orbit of the moon is also a little bit tricky. I'll do that one too. So here's a picture of the moon traveling around the Earth. And it's a little more interesting, or more regular, I would say, than Halley. It's not quite the same random effect. In this case, what's going on with the moon is that as the moon and the Earth travel around the sun is in a different part of the sky relative to both of them. So the moon's motion is severely affected by the way the sun moves. I couldn't think of a way to introduce the sun in this and make it intelligible. But I have to say, for many, many years, actually for 300 years after Newton formulated his laws, or 200 to 300 years, people were extremely interested in the theory of the moon. It wasn't easy to guess at all what was happening. An enormous amount of energy was spent by some of the world's best mathematicians trying to figure this way out. The final solution was found by a mathematician named Delaunay, a French mathematician. Delaunay has a formula. He has a little book on the moon. It's chapter 2, The Theory of the Movement of the Moon. This is the first part of his equation. This is the second part of his equation. Third, fourth, fifth. It goes on for 22 pages. And not only that, it was considered a practical formula. So I mean, nowadays, at best, we would take this formula and try to plug it into a computer, and then we'd have it, wouldn't have to rewrite it. In those days, people worked very hard. Finally, people realized that maybe this wasn't a very productive enterprise, until a French mathematician named Henri Poincaré came along and said that not only was Delaunay's formula extremely complicated and perhaps not so practical, he said it was actually wrong in some sense. Delaunay did not understand what his own formula said. The reason is because, well, it's very complicated. So first of all, he wasn't actually directly predicting the effect on the moon. What he's predicting is the effect on the moon's orbit. So there's some mathematical technique which enables you to tell how other planets affect not just the planet, but the orbit. So at any given moment, there's an ellipse, which somehow is the closest approximation to the orbit of the planet. And there are very simple formulas for seeing how forces affect that. And Delaunay's formula is a formula which tells you the effect on the elements, of the shape of the orbit, so to speak, and other properties. And it turns out Delaunay was under the illusion that if only one worked a little bit harder, we could show that this series converged. Actually, it doesn't converge, and that's what Poincaré showed. It's in some sense only an asymptotic series, and it's only very limited validity for a very, very short time, if any at all. And he showed that by showing some really, really complicated examples, which I'll give you some idea of. So the whole theory, at this point, sometime toward the end of the 19th century, the whole theory of orbit calculations vanished into Poincaré's brain, so to speak. And that actually made a major change. So to give you a hint of how things can really go, I'm going to show this. So here's, down here at the bottom, you can see down at the bottom. So here's Jupiter again, our favorite planet because it's by far the most massive planet in the solar system. And here's an asteroid called Helin. And it's doing its thing, as the other one did as well. Its orbit comes suspiciously close to Jupiter's. You might suspect that it's going to get into trouble. And it does indeed get into trouble. It just gets attracted. I mean, you know what love is like. And there it goes. It comes close to Jupiter. It winds around. It sticks close to Jupiter. It doesn't seem to want to go away like a dog that's following its master on the way to work. It just keeps coming back and coming back and coming back until finally it stops coming back. No, not quite yet. There it is. It's gone. But it's just shifted into a new orbit, and the new orbit is, again, suspiciously close to Jupiter's. And what you very much suspect is that sooner or later they're going to meet again and get involved. There's no question. So I'm going to show you another picture of the same thing. Whoops, I don't want to do that. We have another picture here somewhere. So here is the same picture, but now I've fixed Jupiter. I've concentrated, as I did before with Lexel, I've actually fixed Jupiter. In this case, I've added a little arrow. The arrow is the direction of the sun. So what's going on here is that Lexel, the planet Helin, is not just attracted by Jupiter, but the sun is very, very big and still has some effect on its motion. So we're looking at here, instead of the situation in Kepler's theory, where we're just looking at two bodies that are moving around each other, we have three bodies, and they're interacting in extremely complicated fashion. So if you're standing on Jupiter, the arrow points in the direction of the sun. So here's what's going on if you're standing on Jupiter. This is what it looks like. It's really a very complicated trajectory. What's going on? Just keeps coming back, 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 back. And then it's gone. Disappears off into outer space. So this sort of behavior is what mathematicians find extremely interesting, I would say. In fact, after Poincaré, the whole thrust of mathematical astronomy changed. And, well, it's split into two parts, really. Practical calculation, which we now do by extremely, NASA's supercomputers are fantastic. So most of the practical calculation we do by computer. I think, as far as I can tell from NASA's data, they actually simulate all of the major planets' effects on all other objects by just running their computer time. When I access the data for a planet on the NASA Horizons website, they do the calculation in real time. But that's because they've already pre-calculated tables which allow them to interpolate the tables. Extremely complicated process which doesn't have much theory to it, but it works very, very well. And the other part grew into theoretical mathematics, which became more interested in this question of this sort of thing we saw with Halley's Comet. It's the random effects that somehow planets and actually all dynamical systems have to deal with in some sense. And it became a major theory, and it had a number of major accomplishments, which got a lot of awards during the 20th century, and it's still an active field in some kind. The major question is the following. If you look at Newton's laws, basically Newton has a very simple law. Force is equal to mass times acceleration. And what that means is, if you think about it a little bit more, it says that if you know the planet, if you know the position and the velocity of every object in the universe, then you can predict at some future date of the velocity and position of one of those objects in the universe. Of course, it's impractical to think about, but theoretically you think this works pretty well. If I have maybe 3 bodies, you think, well, I'll just apply Newton's laws and see what happens. The problem is, and the thing that fascinates mathematicians is, this doesn't work for the following reason. You never know the position of something exactly. So if I have 3 bodies, what people now know very well from a huge number of examples is that if I get my data just slightly wrong, then there's no guarantee and no prediction possible of what happens in time. You're guaranteed almost certainly to have a certain random effect like that we saw in Halley's Comet, even if there are only 3 bodies interacting. And this it seems like a very simple situation to deal with, but in fact mathematicians know very, very little about what happens, and prediction on such 3-body systems is almost impossible to work out. They have a number of models. Actually, the asteroids, which I showed before, exhibit some data of that. I won't have time to show you that, but I will show you. So mathematicians worked very, very hard, and after some effort, they've come up with a very simple model that deals with this. It explains somehow in the simplest possible form what goes wrong. This is what's called the Sitnikov system, named after, I believe, a Russian mathematician named Sitnikov who first looked at it. In this system, I don't have an animation. I ran out of time. I have 2 bodies, massive bodies, interacting with each other according to Kepler's laws. And then, in addition, there's a very, very small object, up the little red thing up at the top. It just moves back and forth on a vertical line. These bodies have the same size, so that it's not attracted in either direction. It just goes up and down. And so, for example, you'd suggest that if you start here, it will just oscillate up and down. But as it oscillates up and down, these things keep going around, so the force is closer. The force is much stronger when the objects are here, and much less when they're out here. So there's some kind of random effect, just like you saw in the Halley's Comet orbit. It's exactly the same kind of thing. You have kind of what to this thing appears like a random event. It's like running through a gauntlet. And what happens is that if the object starts far enough away, and there is some eccentricity to the system, then the behavior of the system is now known to be, by a very difficult theorem due to a mathematician named Moser, the behavior of the system is extremely random. In fact, it's almost as random as you can possibly imagine. There's a very simple way of explaining that, which I can't do, however. So, for example, if you're rotating a circle, it's very simple, and you get things that look like this. This is a graph of position versus time. That's very nice. They just oscillate up and down periodically. But if I change my eccentricity to 0.1, and I start getting some wild oscillations for initial displacements which are large, and if I change it to =2, then it starts oscillating extremely wildly, and in fact, the chances are that it will escape. In fact, it turns out, and this again is something that fascinates mathematicians, there's always some hint of wildness whenever the electricity is not 0, but it might be hard to see. Whoops, oh, I did it again. I never log into Google. I think it was So, yeah, there are more models that mathematicians have, but I didn't have time to work them out. In the long run, what are mathematicians curious about? What we really want to know is what happens in the really, really long run in the solar system. Now, you might conjecture, well, the solar system has been around presumably for 5 or 10 billion years. Presumably it's going to last for another 5 or 10 billion years. But actually, we don't know. I mean, there's always a possibility of some catastrophe of some kind. It could be a catastrophe like this one, which is illustrated by one of my favorite artists. He loves to portray solar system disasters. He's a whole gallery of paintings of the same kind where horrible things are happening. Not to people you know, since this seems to be the moon, but he has other things as well. He's got a lot of play on the internet. We don't really know what the longer, even for inside the solar system, we don't really have any understanding of why things just don't fly off or collide or something like that. Mathematicians would like to know that. It's not exactly a matter of practical physics, as some physicist told me last week when I tried to explain to him what was going on. He thought the solar system was very boring. He wanted to know what was happening in other universes. But there are people who worry about this. There's the Planetary Defense Coordination Office. Wonderful. I mean, surely some of you would like to work for the Planetary Defense Agency. I only discovered this very recently. I think it's a wonderful thing. I have in mind actually interviewing one of them just to see what happens. Okay, I'm basically almost through, but before I through, I'll give you a little finale. A friend of mine named David Austin explained to me that I had another PDF animation, and I showed it to David, and he made it into a Java script motivation. This is my favorite simple three. So I've said that any system, any mechanical system with 3 bodies, we really don't know what goes on in prediction. It's very hard to predict how the system is going to behave. This is a very famous system, which actually people know very little about except through numerical computation. I don't even know how Mr. Bureau came up with it. These are 3 bodies. It's a triangle, a Pythagorean triangle of sides 3, 4, and 5. And opposite the side 3, there's a body of mass 3, opposite the side 5, and so on. So these are 3 bodies of mass 3, 4, 5, on a triangle of sides 3, 4, 5. And they're attracted by gravity. They start out absolutely still, and then they start to move. Okay, what's going to happen? I need a prediction. I think that's what the guy thought originally. So there's a huge amount of discussion among the mathematicians of when things just collide all at once, or when they nearly collide and pass through each other. And I think that's what Mr. Bureau thought when he came up with this system. He thought it was just sort of ordinary. But they keep going. When you see the little polygons, so you can see, I should point out, they almost collide, and then you see these little straight segments. Again, that's because we don't want to, we can't slow down the animation, so that's just approximations to hyperbolas. They keep going. Oh, they make a real tangle. But now, as my friend David explained, something wonderful happened. One of them goes off to infinity, and the other 2 go off together. I'm all through. I'm through.